Okay, so this is just a quick little video that explains a few things about molecular polarity. We want to be able to predict molecular polarity because we really need this information when we want to talk knowledgeably about um, physical properties and then differences in those physical properties based on the polarity and then structure of a molecule. So once we get sorted out with molecular polarity, we can bring it into play in terms of the molecular geometry and how those two things will give rise to some different physical properties based on those features. So let's get started with determining molecular polarity first. So molecular polarity really is due to bond polarity. And so if you remember bond polarity, you have to come re-familiarize yourself with differences in electronegativity because that is what gives rise to bond polarity. So you need to look at your table of electronegativities and you determine whether the bond is polar or not. So a carbon-carbon bond, same atom bonded to same two atoms bonded together, so obviously that's going to be nonpolar. There's no difference in electronegativity. A carbon-hydrogen bond, well, this is a little different. Carbon or hydrogen 2.1, carbon is 2.5, so there we have a delta En of 0.4. So there is a difference, but again, that's a small difference. So carbon-hydrogen bonds are typically classified as nonpolar, hence all of the hydrocarbons being nonpolar. Well, how about a sulfur-oxygen bond? Well, here's oxygen, 3.5, small atom, high electronegativity. Sulfur, larger atom, still group 6, higher, not as strong or not as large in electronegativity. And so a difference of 1, that would give rise to a polar bond. And so we then have a bond dipole, and there's a vector that indicates that. How about an oxygen-hydrogen bond? Well, there's oxygen with an electronegativity 3.5, hydrogen 2.1. So the difference in electronegativity between hydrogen and oxygen is 1.4. And so that's definitely a polar bond. Oxygen delta negative, hydrogen delta positive. And that is a more polar bond. The delta En is larger. That would be a larger bond dipole. And so the size of the dipole can also have a bearing on polarity and molecular polarity. So once we got the bond polarity sorted out, we want to take a look at the molecule. And so again, we have to look at the shape. Two things, the bond polarity and then the shape. So again, if we go back to methane, this is methane, CH4. And so methane, again, if we drew the Lewis structure, it looks very symmetrical. You would certainly think that's very symmetrical, everything nice and evenly spaced out. And it is in fact symmetrical. And we can look at the actual space filling model for this and recall that it's a 190 degree bond angle. Well, all of those bond angles are 109 degrees. And so the tetrahedral molecule, when it has 4 ligands, will always be symmetrical. And so that's the case for all of those main geometries. If they're bonded with 4 ligand or the maximum number of ligands, they will always have a symmetrical shape. So then we have to look, once we've determined that the molecule is symmetrical, we look at bond polarity, and we already ascertained that a CH bond is a nonpolar bond. And so if there's no polar bonds, the molecule cannot be polar. So it's a nonpolar molecule. And so methane, as we know, is a gas at room temperature, and a large reason, part of the reason for that is its lack of polarity. It's a small molecule and it's nonpolar, so it's not going to have very strong intermolecular forces. Well, if we change one thing, what we change now is we've taken a hot chlorine or carbon-hydrogen bond and added a fluorine, and we will know that this is definitely a polar bond. And so one polar bond with all these nonpolar bonds on the same geometry. So this is actually fluoromethane. So fluoromethane has the same molecular geometry. It's still tetrahedral, so it's still symmetrical. But we now have presence of a polar bond. And so one polar bond in a symmetrical molecule is going to have fairly large impact. And so we look at it here. So now if I was to draw that polarity or vector, here's my delta negative. Everything else is positive. And so I now have a molecular dipole. And so that's a polar bond or a polar molecule. So molecular dipole or polar molecule. It's also known as a permanent dipole because that molecule is polar. It will always be polar. And so I now have a polar molecule. I have a symmetrical molecule, but one of the bonds is now a different type of bond. It's a polar bond. And so in terms of vector analysis, if you were to do it, you would now see that there is a vector direction to this polarity, this difference in charge. And so that gives rise to a permanent dipole. And that's going to affect physical properties to some degree. Now, the other thing you want to look at is the geometry based on polarity, or the molecular geometry. So another thing you want to be able to look at is then the geometry when you have bond polarity and how that's going to affect molecular polarity, because it does change. So let's first of all assume all bonds are polar. Okay, it doesn't matter what they are, they're just all polar bonds. And so if we look at this first molecule, AX5, trigonal bipyramidal, that's a non-polar molecule, even though all of the bonds are polar. And the reason for that is all of the bond dipoles get canceled out. Again, that's through vector analysis. We're not going to go through that, but you can kind of see it. If I look at this aspect of the molecule, so that's a polar bond, delta negative, but this is also a polar bond in exactly the opposite orientation. And so you can think of that like a tug of war. And this top atom is pulling, this bottom atom is pulling. Because they're pulling exactly equal in exactly the opposite direction, there is no overall pull. And so linear components are typically nonpolar if it's the same bonded atom. Well, in this orientation, I have my trigonal planar option or orientation, and trigonal planar is also a non-polar orientation if all the bonded atoms are the same. And that's because they all separate maximally, 120-degree bond angle, but again, vector analysis would show that there is no direction or magnitude to those polarities. So AX5 or trigonal bipyramidal is nonpolar even with polar bonds. Well, that's going to change as soon as we take one of those polar bonds. Well, that's going to change as soon as we take Well, that's going to change as soon as we remove one of those bonded atoms and add a lone pair. So now I have an AXE or AX4E orientation. Remember, this is now a lone pair. And so that is a seesaw orientation. And so what we've changed is, in terms of polarity, is we've removed one polar bond, but what we've done is we've removed that symmetry in that equatorial region. And so now we basically have no symmetry of bond dipoles. And so a symmetry of bond dipoles is what allows those to cancel out. And so if we lose that symmetry of those bond dipoles, we end up with a polar molecule. And so an AX4E orientation or notation would give rise to a polar molecule provided the bonds are polar. And so that carries through to the next shape we see with the steric number of 5, and that's AX3E2, and that's T-shaped. And so T-shaped, I now have two lone pairs around the central atom. If you look, I still have this linear component, which would still be nonpolar, but now I have definite polarity here. That's going to be delta negative, that's going to be delta positive, because I've lost those bond dipoles that would give me symmetry. And so an AX3E2 orientation would be polar. So the last one is then AX2E3, and I think you'd all see that that is going to be a nonpolar molecule. I now have symmetry, basically, of these lone pairs. But what I really have then is symmetry of the bond dipoles in that linear direction. And so I'm back to this pull in opposite directions exactly equal, meaning there's no overall pull. And so an AX2E3 orientation or linear, we're back to nonpolar. So as I said, you have to consider the bond polarity, yes, but you must also consider molecular geometry. So molecular polarity and hence due to bond polarity is going to give rise to some some changes in physical properties. And so I'll just quickly go over this. We'll look at this again in another video, but just to show you how this then works. So here we have methane, which we already determined was a symmetrical molecule and non-polar. Non-polar because there's no polar bonds. And look at the boiling point, minus 164 degrees. So it's a gas at very low temperatures, and that's because there's absolutely no polarity. Small molecule, no polarity. Well, if we add one chlorine, we have chloromethane, and so chloromethane is in fact polar, and it's polar because we now have a polar bond. A carbon-chlorine bond is polar. And look at the change in boiling point. So it goes up dramatically. That's a significant increase in boiling point. And a component of that is due to the polarity of the molecule. And a component of that is also the fact that we've placed a hydrogen with a chlorine, and so we've increased the dispersion forces quite a bit. But polarity is definitely having a role in that great big increase in boiling point. But you can see how dispersion forces or increased size of the atoms is going to affect it too, because we have carbon tetrachloride here. And look at that boiling point, 76.72. Yet, based on the symmetry of the molecule and the symmetry of the bond dipoles, that's actually a non-polar molecule. So the increased boiling point is due solely to increased dispersion forces. So even though you have a non-polar molecule, size of the atom, size of the molecules is going to have a bearing. And so these are the sorts of things you have to consider with physical properties. So just to quickly summarize, so in determining molecular polarity, there's a few things you have to take into consideration. So the first one would be bond polarity. Okay, so you cannot end up with a polar molecule if there is no bond polarity. So carbon-carbon bond, carbon-hydrogen bonds, all that sort of bonding that gives you a non-polar bond will give you non-polar molecules irrespective of the shape. But if you have a polar bond, you have the capacity or the potential for molecular polarity. You don't always get it, but you can possibly get it, which gives rise to the second thing you then need to consider, and that is geometry. And so once again, we have something like ASF5, which is a AX5 orientation. Even with polar bonds, these are all polar bonds, it's going to be nonpolar, and it's nonpolar because the orientation of those polar bonds, every one of those bond dipoles cancels itself out. Whereas we have something like AX4E with bond polarity, so we still have these polar bonds, but now we have asymmetrical arrangement of those polar bonds. With that lone pair there, instead of a bond pair, we get a different structure, a different geometry, and that geometry gives rise to a polar molecule. And so the physical properties of these two different species will be different because we now have molecular polarity. And so that finishes this video.